Hello, and thanks for joining. My name is Matt Harris, and today I'm going to be covering Scott Folger's Elements of Chemical Reaction Engineering, problem 115B. The reaction A forms B is carried out isothermally in a continuous flow reactor. Calculate both the CSTR and PFR reactor volumes necessary to consume 99% of species A. Also, it lists the concentration of A is equal to 0.01, the concentration of A initial. So that's referring to the 99% conversion. Additionally, it's asking us to solve this problem for two different reaction rates. That is a first order reaction in problem B and a second order reaction in problem C. Additionally, it's giving us some extra information down at the bottom so we can get a head start to our mass balance. The volumetric flow rate entering is 10 decameters cubed per hour. It's also giving us some information on how that was calculated and how to transfer that knowledge to our final flow rate. So, for example, it says right here, the volumetric flow rate is constant throughout, which means the final volumetric flow rate of species A is going to just be a function of the final concentration, which it gives, again, up here initially. Additionally, it's calculating the initial concentration of species A for us, which turns out to be 0.5 moles per decameter cubed. Let's take a second now to format this information in a much more approachable way through a diagram. Okay, now we have it all formatted in a diagram that's nice and easy to read. So as I mentioned previously, we were missing one piece of information, and that is the final concentration of A. For the concentration of A final, how we find it is using the extent of reaction variable x, which we are given in the problem statement to be 0.99. As a result, once we plug it into this function, C sub A is equal to 1 minus x C sub A initial, we get the answer of 0.005 moles per decameter cubed, which we will now insert into the diagram to solve future problems. For problem B, we're working with the rate function, negative r sub A is equal to k C sub A. This is a first order reaction with the constant k is equal to 0.001 seconds to the negative first power. The first step in solving this problem is converting seconds to hours. This is because if you look at any of the other flow rates that we're working with, it's all in terms of hours. So we're going to quickly multiply 0.001 seconds to the negative first by 3,600 seconds per hour, giving us a new rate constant of 0.36 hours to the negative first. The first thing we need to do when calculating the volume of a CSTR reactor is getting this function, which is found on table S-1, page 25. Once we have this function, all we need to do is just plug in information that we already have. So first we need to substitute in the rate constant that we found in the problem statement, and then we substitute in the other information we made in our previous diagram. Finally, we get the resulting volume, which is 2,750 decameters cubed. In order to find the PFR volume for the same reaction rate that we were given in problem B, we need to find a similar equation as the one we found in the CSTR version on table S-1. This results in the equation dF sub A over dV is equal to R sub A. Now, the next step that we need to do is start substituting. This equation that I've highlighted right here is a variation of the one given in the problem statement. That one was F sub A is equal to V C sub A, but all we've done here is gotten the differential form of it. which, since the volume is constant, or the volumetric flow rate rather, is constant throughout the reaction, uh, it will result in V d C sub A being equal to d F sub A. Additionally, we have the reaction rate given for this problem, and we're going to substitute that in as well. Okay, once we substitute those in, we get the equation V d C sub A over dV is equal to negative K C sub A. Once we move this around a little bit, we get it in a much nicer form for integration, having dC sub A over C sub A and dV both isolated for integration. Then once we move into the integration, we set our bounds of C sub A initial and C sub A final, along with 0 and V for our volume. Overall, once we finish integrating, we're left with the form V over negative K natural log of C sub A over C sub A initial is being equal to volume. Once we plug in all of the values that we had in our chart, we're left with a volume of 128 decameters cubed. For problem C, we're going to be doing a different reaction rate. That is negative R sub A is equal to K C sub A squared with a constant of 3 decameters cubed per mole hour. Now, besides that, all of our system is still the same, and we're again going to be doing it for a CSTR and a PFR. For our CSTR, you might notice it's exactly the same setup as the part B solution. We're going to get that formula from table S-1, page 25. As you can see, we have a different rate, and finally, we're just going to substitute it in, making sure we get that squared function, and get a different volume of 66,000 decameters cubed. Calculating the volume of a PFR for this new reaction rate, it's going to be similar, but we're going to have a slightly different integration. Again, getting the formula from table S-1. Substituting for these two functions, except you might notice, again, we have a C sub A squared. Substituting that in, isolating C sub A's for integration. And finally, setting our bounds, C sub A initial, C sub A final, and 0 and V. Once we finish integrating, we're given this function, V over K, parentheses 1 over C sub A minus 1 over C sub A initial is equal to volume. Once we plug in all of our values, we're left with a volume of 660 decameters cubed. One last little note, if we go to table S1 on page 25, we can see that the CSTR and PFR equations can be found under the algebraic form and the mole differential form. So for our CSTR, we were using this equation, and for our PFR, we were using this equation. That should be it, and thank you for watching.